All right, for class on March 3rd, I am putting up the recording instead of working out our tech issues at home, so hopefully we're back to live tomorrow, but this video will stand in for the 12:20 lecture today, March 3rd. We want to introduce a new kind of conic section, so here's a picture of it from one perspective. I got to work through this in a few pieces here, but the picture that you're seeing now is a parabola. Of course, it's the old familiar parabola, right? This is actually just y equals a. Well, I put in 1 for a. So this is just y equals x squared. Good old-fashioned parabola. But I want to think about it from a geometric point of view here. What happens when something, say light rays, might be coming from straight above into a parabola like this, and I just set this up. Okay, so there's some technical stuff in here that you don't need to think that much about where I had to do some geometry, but the concept is that this angle of incidence and angle of reflection are the same. When something hits a surface like that, it deflects out with these angles matching. So this parabola is going to push things into the center a little bit, and wherever it hits, it's a slightly different angle here, but it's going to bounce toward the center there. And of course, it's the same on the other side. If it hits this at a greater angle, it's going to bounce toward the center. But the one interesting thing that happens is there's a particular important point through all of this, that no matter where that line hits this, if it comes off with the proper angle there, they're all going through sort of a pivot point right there, something we call a focus. And that ends up being at a over 4 on this thing. The a is 1 for this example. So this point right here is, we call the focus of the parabola. And it's works like a focus in the sense that if you have a reflector up and there's sunlight coming in from straight above, it's going to focus on this point. You'd get a really hot spot right there. This can be used for a solar collector then, but it's also used in satellite reflectors, because it might not be, a satellite might not be coming from straight above, but they're all coming from one direction. And if you have a parabolic shape, it'll reflect all of the signals that it's getting back toward a single point, where you can put your receiver right here and get a wide set of the energy that's, or the signal that's coming in from the satellite. So parabolic reflectors are what satellite dishes use, and it's rotated around to be three-dimensional, but it's based on this property. Now, we're not going to dig through all the geometry of these angles. We're going to approach this from another geometric perspective, talking about the distances that show up here, and I'll go on with that on paper. Okay, the distance relationship, I want to think about this a little different. We're going to do a lot with the distance from a point, like a circle does, where the distances from two different points. We're going to do some comparisons on that, but this is a different kind of distance relationship. I'm looking at, what if there's a line out there somewhere and a point that's not on the line somewhere else? It's going to be on one side or the other, right? What if we look at the points equidistant from these? From line and point. So there would be one that would be on there that would be halfway between them in a straight line. There'd be a point right there. But there would also, if you go a little further away from the line, you could also get a little further away from the point. And somewhere like out here might work okay, because this distance might be the same as, you're talking about the distance, perpendicular distance from the line. So as that grows to a little more and more, you got to get a little further from the point also, so you're going to get some kind of a shape that includes certain points out there. The distance from the line is equal to the distance from this point, and you would have points on both sides like that somewhere out here, where this is the same as that. So we get some kind of a curve from that clearly. I want to take a look at those using the technology, and then we'll work it out what the distance formula tells us about the equation of this thing. As an example, this kind of conic section, this is the points that we're looking at. And we'll see what this kind of shape does using this software. Okay, so the line and the point that I picked for this one are shown here in green and blue, and I'll zoom in here a little bit, I guess, because I picked them pretty close together because I'm working for the equation to come out nice. But you could do this with different points. But I picked a line y equals -1/4, and the point 0, 1/4 is like a point on the y-axis up here. So I had those equidistant. So the one point halfway in between, or where the distances are equal, is going to be halfway in between them right there at the origin. So I set this up so that that point, what we call the vertex, is at the origin, which is nice. But then there's going to be other points out here. I want the distance from the blue point to be the same as the vertical distance from the green line. And so I set up these equations, and this is actually familiar. This is circles with a certain radius centered at that point 0, 1/4. So that's going to be circles coming from here. Once I put in a positive radius, you'll see circles around that. Distance from that point being capital R. And the distance from that line being capital R is just subtracting the y values. If you're talking about the straight up and down distance, it's just the difference in the y values from y to the -1/4 value where my green line is. So I set those up. Now if the radius is too small, those don't come together at all. There's no points where those match yet, but as we get bigger, when I get up to the 1/4 mark, those two lines would come together at the origin. And as I get beyond that, there's intersection points out here where the distance from the blue point is the same as the distance to the green line there. And as you get further out, you can see those points still intersect out here. We're interested in where the red and purple things intersect. That's equidistant from those two things. And it's going to sweep out kind of a shape. They keep in touch in this corner, and in this corner it's kind of symmetric here, but you're getting points from the origin out to points like this. And you see when you get out to intersection point right there, that looks like when it hits y equals 2, it looks like the square root of 2. You might recognize that if I go out a little further. When I get to, for this is going to be going upward because my point was above the line, so these are going to be going upward from there. If I get out to when y is 4, you get points like, I'm pretty close to it there. I don't know what the r value is going to be a little different, but we're getting out to around 2, 4 there. So it's following points like y equals x squared. It's forming a parabola. If you watch what happens to that intersection point as this goes through the operation here, it's going from by the origin right there in both axes coming out and sweeping up in that kind of a shape that looks like a parabola. And it is a parabola. All right, we're going to see why that's true. Okay, so I should be able to do the rest of this on paper. Okay, this is the one we were just looking at, and I'm drawing in the points in blue here where this happens. So the distance from this 0, 1/4 is the same as the straight line distance from -1/4 up. Goes through the origin and ends up following this graph. Here's y, and I don't need to go through this in terrible detail because I'm not trying to do fancy proofs here too much, but the distance formula is the square root of this. That's the radius of that circle that we had before. So that's the distance from xy to 0, 1/4. And this is the straight up and down distance from y to the 1/4. For those to be equal, well, I squared both sides here. And then I just did out the algebra. If you do out the y minus 1/4 squared and the y plus 1/4 squared, multiply those out, we're getting some weird fractions in there. But a lot of the terms cancel out, and this kind of simplifies down to x squared minus a half y equals positive a half y, or add a half y to both sides, you get, sure enough, y equals x squared. So that's the familiar old graph of y equals x squared from the perspective of these two distances on there. So this, we've gotten used to maybe calling this the vertex on a parabola. And there's a way to find that. There's also key points geometrically. This one out here is called the focus. And this line down here is called the directrix. And for any parabola, there's also going to be a focus and directrix. If it's a true parabola shape, there'll be a point kind of inside of the curve and a line on the outside of the curve, same distance in between here. And the relationship we're going to end up seeing algebraically is that we call this distance A. I believe they use A in this book. It's A. This is the same distance in the other direction because the vertex has to be halfway between them. It's equal distances. But this value A from the focus to the vertex or from the vertex to the directrix in that direction is related to this. And what we have is x squared equals 4ay. Anything in that shape, anything in that form is going to have an upward parabola shape. It's going to be equally distant between the line y equals minus a and the focus at a up here, this distance. Now if a is negative, the focus would be below and the directrix would be above, and x squared would always be negative. We'd have a downward parabola. So this is an upward parabola shape if a is greater than 0, and downward if a is less than 0, would be a downward parabola. Can't have a equals 0, that wouldn't leave you with anything. Well, if a equals 0 and this x squared equals 0, and you don't really have anything going on. So, parabola upward or downward in this case. Now, we're not really going to do a diagonal line situation because this would get crazy if you do diagonal lines. You can draw it, and we are getting some kind of parabola out there, but the equation of that thing would have an xy term in it, and it would be an ugly kind of equation. We're only doing horizontal and vertical ones. And if you do this with a vertical line and a point that's not on the vertical line, you can do the same kind of game here. You're going to get a different looking equation. You can do it in black here, but the halfway point would be there. This would be the vertex. This is the focus and directrix here. Vertex would be halfway in between. Parabola would end up going this way. It'd be a sideways parabola. We're going to build those in because those are a nice conic section. And if you're set up with the x and y axis being here, and that's kind of a convenient way to do it, where that's your x and y axis and the vertex is at the origin, those are the kind we're tackling first. Vertex at origin, the focus for the sideways one, the focus is over here on the x-axis. The a value is the x-coordinate there, and it's on the x-axis, so it's at a0, and directrix is the vertical line. X equals the opposite of a. In this case, I picked an a that was negative, so the negative a is a positive number, and that's x equals something over here. The parabola is going to be sideways, so we're going to get a sideways parabola opening to the left if a is less than 0, and we're going to get a parabola opening to the right if a is greater than 0. That's what ends up happening with those. So if you can find this a value, or if you're given this stuff, you can get the a value easily. That a value is the key to the whole thing, but you have to know the form of the equation. It's convenient form, like we had for lines and circles, a convenient form for the equation. And for these sideways ones, it's a y squared equals 4a times x. So that's like x equals y squared would be a sideways parabola. You could have different ones go in one direction. Notice if a is negative, you can tell the x has to be negative in order for that to come out to a positive value like that. So that's going to be the ones that only go to the left or open to the left. Opens left. And this opens right. If a is greater than 0, if you have a positive there, then x also has to be positive to come out to a perfect square. So that works out okay. We can go from the equation, rearrange it into this form, and tell what a is. And if there isn't any other terms, then this will go through the origin. They're both 0 at the same time. It goes through 0, 0. So if there isn't any other terms in this, then we have a parabola at the origin. If you just have x and y squared, or just y and x squared, you have a vertex at the origin, and we can work out the sketch on that. So if I start with y equals x squared over 12. If you remember, like the algebra approach to these things, you could plot some points or think through this as a version of y equals x squared. It's going to be kind of a flattened version, but we're going to see how it works from a conic sections perspective. If we put it in our x squared equals form, the form for these kind of things, this is has an x squared term in it, so it's in this form, or we want it to be in this form. X squared equals whatever's sitting here has to be the 4a. So this one, if I get the x squared by itself, I'm doing times 12 on both sides to get x squared by itself, and I got 12y. So my form is x squared equals 4ay. That means 12 has to be the 4a, so a equals 3. So this would have, from what I know off from this form, vertex at 0, 0. 3 units in either direction is going to give you the focus and directrix of it. This is positive, so it's a parabola opening up. The focus is going to be above. The focus is 3 units above the origin. Directrix is going to be below by 3 units. So it's the line y equals -3. This isn't a point, it's a line. So we put it as a line equation. Those two things we can determine just from that. So if in this setting of this great big complicated looking second degree polynomial thing, we're looking now at situations where one of these squared terms is there and the other one's not. So one of those, one or the other, is equal to 0. So we'd have stuff like, well, let's do the 0 sitting here. So if I have, and again, we only tackle the ones without the x, y term. So let's do one this way around. What if this is 3y squared plus 5x and actually we're doing situations now where the other terms are 0. If we start getting some non-zero stuff here, we're going to move away from the vertex at the origin. So we're starting with these simplest cases and then we're going to work in some of this stuff. But if that's all I've got, then I can put it in this y squared equals form or x squared equals form. In this case, y squared equals. So 3y squared equals -5x. Y squared equals -5/3 x. So that's matching up with this form, the sideways parabola. So 4a has to equal -5/3, or a is -5/12. So I got that negative value right there. That means, well, it's a y squared thing. And if a is negative, that means it opens to the left. I'm getting a vertex at the origin. I'm getting a focus to the left of that by this amount. So -5/12 still on the x-axis. So x is -5/12 and y is 0. Is the focus of it. So that's where you'd want to put your receiver if you're doing some kind of reflective satellite dish or something. The directrix is on the other side, which is not as useful in applications, but that's all that's out there. +5/12 direction, x equals +5/12. So we can write down that information coming right off from the equation. Now if I have some of these other terms involved, I want to see what that does. So I'm going to work through one of the more involved situations. What if we have no y squared term, but we have an x squared term? And we have a y term. Maybe we also have like an x. I guess what I'll throw in next is a constant term. Let me throw in a constant term now. We'll do one with an x term also, but this is just as x squared y in a constant term. So that's a little weird. Solving it for y, we could get a familiar kind of thing that we could plug numbers into and graph the equation that way. We could do this the old-fashioned way, but knowing our expertise now with conic sections, we can do this by using our conic sections thing. If we have an x squared and no y squared term in it, then we're trying to solve for x squared to put it in that x squared form. We got to deal with this, so we'll see what happens. 2x squared equals negative 5y and a negative 12 if I rearrange it to get this by itself. Divide them by 2 everywhere. X squared equals negative 5 halves y minus 6. Now I have an extra term in this, so I'm not getting x squared equals 4ay. What I'm going to have to do instead is get x squared equals 4a times y minus k. There's going to be another term out here. And that means my vertex got shifted. If you replace the y with a y minus k, the vertex gets shifted by k units. And so now the vertex, instead of being at the origin, is moved up because I got that extra term. So instead of just y and being 0 when x is 0, it's y minus k, and it's going to be, well, it's going to be y equals k when x is 0. It's going to have a vertex at k 0. It's going to go through that point, and that's going to be the vertex of the thing. But I have to figure out what k is. So in order to make this look like that form, I have to sort of factor out the negative 5 halves. It doesn't come out neat like this, but I have to divide them both by the negative 5 halves. So I have to get the parentheses where they belong. I'm going to write this as negative 5 halves times y, and negative 5 halves times, well, I got to think about what negative 6 divided by negative 5 halves is. So it didn't factor out neatly, but I have to divide it out anyway. So work out that division problem. It's 12/5. Take out the negative. These are going to be both plus. It's y plus 12/5. So k is negative 12/5. So my vertex is at negative 12/5, comma 0. And the a value, I'm just matching stuff up. So I'm just matching this up. That's how I got that. Now I got to match this up. 4a has to equal negative 5 halves. This is higher level algebra thinking, matching patterns like this and using what we know. But this is in that form now, and the 4a is equal to negative 5 halves, so that means my a value is negative 5/8. If I have an x squared term and a is less than 0, I'm looking at a downward parabola. Now the vertex is here. The focus has to be below that by another 5/8. What happened to my lighting? That's weird. Okay. I gotta be another 5/8 below that, so I got some pretty cumbersome numbers on here. But this is gonna be 5/8 down from there, from that point. So negative 12/5 minus 5/8. I just want to get decimals for those so I can make coordinates of it on the graph. So this is negative 2.4, comma 0. Another negative 5/8 on it. So negative 2.4 minus 5/8. Could have worked through some that came out nice, but this is negative 3.025. 0 is where the focus is. Directrix is 5/8 above that if you need it, but you can make this sketch pretty well from here. If you know where this point is. That's on the parabola. The focus being down here below it by a little bit means the parabola's coming out in that way toward, wrapping around the focus like that. So that's the basic shape of it. I could get some other points if I want to plug in some x values. I could see what else is going on out here. If I want to sketch it more carefully, I should see what happens at like x equals 2 or something. You can plug that in anywhere, this form of the equation. So 2 squared is negative 5 halves y plus 12/5. Once you plug in one number, you can solve for the other one just doing the algebra out. So this is 4 I could go ahead and distribute this now. I don't know why I picked this form, but that's my -6 again. Add 6 to both sides. I'm trying to do this quickly because you can take your time if you want to think through the steps. It's a video. -5/2 y equals 10, so y equals divided by 5, -4. So it goes through 2, -4. That's another point down here, and it's symmetric about this line that cuts through the focus and vertex. It's going to do the same thing on this side, so it would also go through -2, -4. You can get another point for free, and you get the basic sketch with a few of the key points marked. This is -2.4, comma 0 is important. Those points, and we know the focus coordinates also, although that point's not on the parabola, it's kind of inside of it there. Now I'm going to put off for now what happens if I throw an x term in there also, then we're going to have to do completing the square stuff. And I'm going to put those off for now, try to get the basic ideas of it down. So you can put things in this form and get the vertex and focus from things in this form. If they have just an x squared or just a y squared term, this is the forms we're looking for. That's what we got to try out first. So we'll give some of these a try, and we'll talk more as we go along about what happens if we move this around some away from the vertex being at the origin like this.